All right. So my name is Zachary Lowery. I currently work for Leading Edge. They've been a fantastic employer. A whole bunch of them are right here to give me a hard time. I did provide a QR code if you guys want to follow along. The presentation has a lot of links in it just to reference what I'm talking about. The talk itself is kind of a sky-high view and was originally designed to be interactive. So if you guys who are in here with me have some questions, don't be afraid to ask those as I close up or start up a new slide. So I have given this talk once before at the Leading Edge office. We do have quarterly talks, which are very awesome. And if the QR code didn't work for you, there's also a link if you can catch that in time. All right, just a disclaimer. I didn't want this to be a definitive, here's the best way to do IoT with a CI or CD or some kind of pipeline. This is something that worked for me, and being it was more of a personal project I did after hours. I wanted to ensure a high level of quality, but I also wanted to make it easy on myself. So I'm going to have a lot of recommendations, a lot of things I tried out that didn't work, that I found alternatives to, but may not scale to a full development team. Or maybe they will, we'll see. We'll be covering a little bit about IoT on the Raspberry Pi Zero W, primarily. I chose Node.js, so there's going to be talk about that as well. I'll try and cover some holes if we have some people who aren't familiar with that framework. I did rely on dependency injection and unit testing to ensure the code quality. And I did throw in some cross-platform development somewhat, and we'll get into that later. And a large portion of the later part of this presentation is about GitLab, which I actually love. I run it at home, and this relied on my infrastructure at home, and we'll talk about that. So the story starts with my friend named Anthony, who reached out to me one day. He has a cousin in Montana he owed a favor to. And while Anthony likes building with hardware, he's not much of a software developer himself. So his cousin owns a cricket farm. They grow these crickets for alternative food products. They mostly use them for cricket flour as an alternative to wheat flour. And since they grow so many of these crickets, they needed to monitor their health, toxic gases, because the urine from the crickets does build up as ammonia. More crickets in a bin that they raise them in is more temperature, a higher temperature. It's very hard once you have these crickets at scale to actually keep them healthy. So I started looking at what Anthony had built. He had chosen the DHT22 temperature and humidity sensor. He had used the MQ2 gas sensor, and they already had an AWS infrastructure set up with DynamoDB. So I was looking at the different libraries available to me, and they all had Node or JavaScript libraries. They also had Python libraries as well, and AWS has a lot of clients or client libraries for different languages and platforms. But I had a little bit more familiarity and comfort with Node, and I thought it would be fun to make this event-driven Node project. So I went forward with that. So the thing about Node is, while a lot of the Node libraries you might run into or use in your projects are actually just JavaScript, you can have native libraries. These are libraries that actually have some kind of C or C++ hook into the Node v8 runtime, and then can, of course, depend on whatever else you want on the system. And I've included the libraries I've found here. I ended up forking a lot of these for my purposes. A lot of them depended on CoffeeScript, which actually broke, or at least the version of CoffeeScript they used broke in Node 10. So as part of my efforts to migrate from Node 8 to Node 10, I created decaffeinated forks of these, which I am attempting to maintain in my own time. So supported hardware, obviously the final device we were using was the Raspberry Pi Zero W. But I wanted to make sure this ran on the Pi 3 in case we needed more horsepower someday. And of course, I'm developing on this x86-64 laptop or desktop, and I needed to be able to run and test my code there as well. So The Raspberry Pis use this system on a chip design called the BCM2835, but they do use different processors. The Pi 0W has an ARM6 processor, which has no hardware float capability, and the Pi 3 has an ARM v8 processor. And I'm not exactly sure how different the binaries are going to be between the two, but I thought some independent building and testing on these devices was in order. So I did include that in my plan. So the first thing I ran into was we needed this BCM2835 header. This actually allows the Raspberry Pi and applications on the Raspberry Pi to communicate with the GPIO pins. And unfortunately, that's not a Node package. And I kind of like having my package manager manage all of my packages and dependencies. And fortunately, someone wrote a project called Napa, which I used to make sure that that was automatically downloaded and included in my Node modules folder, even though it's not exactly a Node module itself. If you end up downloading an archive through Napa, it handles extracting it for you. So it basically treats it like any other Node module. Reading the DHT22 is an asynchronous operation, but the library itself was not written with promises in mind. So I wanted to take advantage of async await. So I ended up wrapping these asynchronous functions. And you'll see that a lot of the time with these libraries that there are asynchronous functions with callbacks. And if you want to take advantage of async await, you do need to wrap them in a promise and return the promise at the end of your function. Mocking the sensors was something I decided to do in order to get it working on my development machine and make unit testing easier. I ended up writing a function that returns a random integer. And what I ended up doing to make these random functions testable was I also eventually ended up mocking random itself, which is actually a valid way of doing so. Making sure you can unit test with unknown values. You write a fake random and have it return a static or known value, which is even more random, right? For the actual mock, I actually had it represent the maximum 2-second timeout that the GPIO sensor, the DHT22 sensor has, just to make sure that the asynchronous code was executing in the right order. The MQ2 is a little more interesting. This is actually an analog sensor, and we had it on an analog to digital conversion chipset, the ADS1115. So what I'm not showing here in this code sample to make it more abbreviated is that I actually ended up writing a scaling function that will convert this analog signal to a digital representation of the voltage, which then gets converted to how toxic the gas is in a particular area. Same thing, I'm wrapping the async function from that library inside of a promise as well. And it has a very similar mocked version as well. AWS has Dynamo storage, likewise wrapped in a promise. That was relatively easy to mock out. With the doc line, I was only using the put function. Injecting an alternative to AWS's library was relatively simple since I was using such a small part of it. So I got a first version together, presented it to Anthony. He liked that it actually worked, but he didn't like that he had to manage the Wi-Fi connection himself. And the Raspberry Pi, if you're familiar with it, has the Raspbian desktop environment, and trying to run that on a Pi 0W is kind of slow. We wanted to lock in the user experience a little bit more and actually provide a method for this application, now called Elise, based on request from Anthony, to manage the Wi-Fi connection itself. So I actually did manage to find this Node Wi-Fi package, this Node Wi-Fi package along with a user input package to manage the Wi-Fi connection. And we ended up with this mini-driven command line interface with Inquirer, which was the input library that we used. And it provided a method just to list Wi-Fi networks, collect the password that typed in by user input. And while not an ideal user interface, we felt it was serviceable enough to distribute to the people who would be raising these crickets or helping work with these crickets. I ended up going with a similar-ish to an MVC design full with views and controllers. The controllers are dependency injected, and do manage, or have the dependencies are managed external to the controllers are instantiated with the dependencies. We get a little bit of inversion of control with that. But Anthony wanted more. So if you've ever worked with a Node project, you know that you end up with this massive Node modules folder with all of these different files. If you're copying these files around or deploying them in an environment across the internet or even on a file system to another file system, it can take a while. So I looked into a project called Nexi. There's a similar one called Package if you are interested. They work pretty similarly, but what I liked about Nexi the most is that it actually does support embedding native Node modules, which Package I don't believe has support for yet, or at least it didn't at the time I was working on this project. I added a package JSON task to spit out the binary, so you could just run npm run build and get what you expected out of that. And there's some benefits to this that I feel need to be mentioned. You get a single file deployment. Everything is wrapped up in a single binary. The embedding of the native Node modules was really handy. I didn't have to worry about those. Your Node runtime, if you build it off of version 6, 8, 10, whatever, you get to bundle that with your application, and then you can upgrade your runtime at any time, or if you find that that doesn't work for your project, you can always downgrade. You get to replace your runtime along with your application if that's ever necessary or useful in your situation. So now that I had all of these packaged JSON scripts, I have this build. How do I ensure that all of these IoT devices we're building for these crickets don't break or don't fail in an upgrade or really cause a big headache for us? We can't go out to all these different sites or different people and help them individually with these devices. So I looked into using continuous integration with my own personal GitLab server at home. And I actually really loved GitLab. It's self-hostable. Most of it is open source. It is sort of like a self-hosted GitHub, but you get the CI/CD piece optionally if you install the runners. And the runner is a separate package you can install. They recommend that it be installed on a separate server, but since it is just me, and I only have one server at the moment, I am running my GitLab runner instance on the server. But I am also running them on the Raspberry Pis as well, at least 2 examples of, and I'll get into that in a little bit. With the CI pipelines that GitLab offers, you have 2 options. You get this GitLab CI YAML file that goes into your repository, or you've got Auto DevOps. And Auto DevOps is sort of an opinionated way of doing DevOps. And actually, I should say continuous integration and delivery. DevOps is more of a process, as one of my coworkers was quick to remind me. But with Auto DevOps, it works with Kubernetes, Helm, which is sort of a package manager for Kubernetes, Docker, GitLab Runner, of course, and Prometheus. That way you can monitor your deployed solution through your actual CI pipeline if you decide to do so. The GitLab CI YAML file offers a few other options as well. The runner can run in an SSH or a shell mode, where it either runs on the same machine that the runner is on or communicates with another one over a network via SSH. It works with Parallels, VirtualBox. There is a Docker workflow and a Docker machine workflow, and also integration with Kubernetes. The CI structure is comprised of pipelines, which are comprised of stages, which are comprised of jobs. That seems to be a relatively standard hierarchy for these things as far as I can tell. So I don't think that should be too different from any other CI system you'll run into. Now the GitLab CI I ended up building for release was a shell runner composed of a setup, analyze, test, build, and stage step. I ended up going with a shell executor because I needed to make sure that the BCM 2835 headers were installed, mostly on the Pis, and I ended up using a virtual environment for the actual installation of Elise into just a controlled environment. Nowadays, I would probably use Docker for that if possible, but at the time I was still using Vagrant. You may need to set up a cache configuration, especially if you have dependencies. The area that your repository is checked into is wiped between jobs. So if there's anything you need to preserve between jobs, you need a cache. Now the downside to a cache is it is a per machine cache. You cannot rely on this to be available on other runners that you have available or other runner hosts. One way around that is to make your dependencies an artifact, and artifacts can be shared amongst hosts. But in my case, I was locking down these pipelines per host via a tagging system. But we'll get into that in a little bit. The setup stage handles installing the NPM dependencies. I ended up building, installing the BCM 2835. Now, unfortunately, I did have to do a rebuild because the NPM install fails when it tries to link with that library the first time. So if it is the first time a runner is running with this task, that rebuild step is necessary at the end, even though you've already installed your dependencies. And I ended up, you really shouldn't use sudo during these build processes, but that was the only way to get the header installed, and ended up making a locked down configuration specifically for the runner and its user. And that is basically the only commands that it can run with the sudo command. The analysis step just runs a lint on the code and also the NPM security audit. Test runs the unit tests and gives us a report we can actually keep as an artifact of our build. The output is put into the build log and also an HTML report, just so you can see it in real time if you need to, or see that record through the web interface of GitLab. If you have a team, that might be useful. There's the build stage, which ends up running my build task I specified in my package.json. This does work cross-platform, in case I didn't mention that earlier. So Linux, you get an Elise executable. Windows, you get an Elise.exe. And it ends up pulling down the version of Node you specify in your Nexi config. Now I have a virtual staging step set up, which ends up running the actual install script I came up with. That way, it actually does bring up a copy of Elise with mocked sensors inside this virtual machine, make sure it actually comes up appropriately, everything runs correctly, and then at the end it destroys the virtual machine and cleans up. GitLab CI has this awesome before script, after script that you can use to set up or tear down various steps. And like I mentioned earlier, there is a tagging system. You can give tags to your runners. So the way I had this set up was that the Pi0, which is ARM6, and the Pi3, which is ARM8, end up doing the setup, analysis, test, and build. This tests Elise in its native environment with the sensors and with the GPIO headers. And then virtual staging runs through the install script in a disposable environment. And like I mentioned earlier, it tears that down at the end, so there's no trace of it left on the server once that's done running. And for my home setup, this is a visualization of my setup. I do have a Pi0W, a Pi3, and my little Intel Nuke server that handles all of this CI pipeline for me. And just to give you an idea on how I arranged my tags, I ended up doing tags for the architecture of the processor, the operating system. If there are any build dependencies I had, those are mentioned in my tags. And if you end up with a lot of different runners or a lot of different hosts with a lot of different runners, this can be useful for narrowing down your build targets. The final pipeline for the entire project looks a little bit like this. You can see that the Raspberry Pis go through their process before finalizing in virtual staging. Now, I was not involved with the project from beginning to its full end, but if I were to continue from this point, I would look into probably using Docker to deploy Elise along with probably something like Ouroboros with a long interval so that it would automatically update. As long as your Docker repository is public, you can basically use Docker Hub as a free distribution network. And in order to mass produce these devices with pre-programmed SD cards, I would probably look into something like PyBakery, which I just learned about not too long ago, that allows you to build a custom Raspbian image for a Raspberry Pi. So That is of crickets and continuous integration. If you guys have any questions about my setup or want me to revisit anything, please let me know. Nothing? Question?
Are there any alternative solutions to what you had to put together by hand for what your friend needed?
There were a few other devices that were centered around beehives that we looked at. Unfortunately, they required sort of an on-premises server of sorts, and were actually very expensive. We were trying to hit a very cheap price range for to attract less technical people to the project. I think we were aiming for about $20 per device, and everything else out there was vastly more expensive than that. Andrew. So, funny story, Node does not distribute an ARM6 version, so I had to compile Node from source on the Pi 6, or I'm sorry, the Raspberry Pi 0W on ARM6. That build takes about 3 hours, so I ended up caching that out once it was done. But that was a challenge I ran into. The Raspberry Pi 3 takes about an hour, so about 3 times as fast. Yes? Python was definitely a close runner-up. A lot of the libraries were available with Python. I wasn't as familiar with the language, and I didn't want that to hurt my startup time on getting the project out there. Yes? I didn't actually intend bringing that up, and that's a good question. So I was actually having some trouble getting Nexi working with the Raspberry Pi toolchain. It always wants to default to the platform it detects itself running on. And there ended up being a lot of path substitution I had to do, and I still never got it fully working, unfortunately. All right. Is that it? Oh, Andrew. I did look into that a little bit. They already had sort of an infrastructure decided upon that I was trying to fit everything into. And we did have the option of using something like an Arduino to measure the sensors and post those somewhere. But they also wanted to be able to add features to these devices over time and included that self-updating mechanism. Mm-hmm. All right. I think, I'm not quite sure what happens now if there are no more questions. Yeah. All right.